slow speed or for less number of interconnected voids in the medium, we only use Darcy's law, which is an empirical relation which has been obtained as a result of the experiment done by Darcy. So these are the three governing equations which are used very often to describe the fluid flow in a through a porous medium. First one is the Darcy's law, which is the first ever empirical law which was obtained by Darcy. According to this, the seepage velocity inside the porous medium is proportional to the pressure gradient across the medium. And when we talk about external flow, then this gravitational force also comes into picture. Second is Forsheimer equation. It is a modified version of the Darcy's law when the velocity is higher. When a non-linear drag is also there in the medium, then in that case, we use Forsheimer equation instead of Darcy's equation. And when we have the permeability of the medium as very high or comparatively high, then in that case, we use Brinkman's equation. So this is done in account of the kinetic dissipation of the kinetic energy due to viscous shear in the medium. And here, this term is taking account of the non-linear drag in the system. CF is the form drag coefficient. So as I said, I'll talk about the preliminaries first. So these are some of the governing equations which we use when we talk about convection in a porous medium or convection in a fluid flow through a porous medium. So the first one is the equation of continuity, which is a conservation of mass, which is based on the conservation of mass, which is based on the law that mass can neither be created nor destroyed. If we have incompressible fluid, then we have a simplified version of this. Then the second one is the momentum equation. And as I said, we can have different versions of Darcy's law, which can be used to govern the motion of the flow inside a fluid saturated porous medium. So the three cases I just discussed. First one is for seepage flow for very, very low permeability in the medium. Second is for a higher velocity when we have comparable obstacle by the solid present in the medium. And the third one is for higher permeability of the porous medium. And all of them are done in account of gravity for gravitational terms, which means we are talking about the external system which is exposed to the force of gravity. Third is the energy equation. It is based on the first law of thermodynamics, where we know that energy can neither be created nor destroyed. It can just be transformed from one form to another. So the first one is the energy conservation equation in the solid phase in the porous medium. In porous medium, we have two phases. One is solid and second is a fluid phase. So the first equation is the conservation of energy in the solid phase, where this term is the heat regenerated per unit volume in the phase medium. Second equation is the energy conservation for fluid phase in the medium, where pi is a parameter which describes the porosity of the medium. Now, very often we discuss about Darcy-Winard convection considering local thermal equilibrium inside the medium. It can be the other case also. We can have an equilibrium also. Then in that case, we'll have two different equations for a single medium which has two different phases. But now here that we are considering local thermal equilibrium, so we consider the temperature of the solid phase as well as the temperature of the fluid phase as same. So in that case, the two equations which I just showed will be combined together and takes this form, where again these terms Km, Qm and this rho Cm have their respective meaning. So this is specific heat per unit volume of the medium. Now it's not a specific heat of a solid phase or a fluid phase. It is now of a medium. Then thermal conductivity, and then heat generated per unit volume of the medium. So this is how they are related with the respective quantities in the solid and fluid phases. And the last one is the concentration equation. When we have multi-component system, when we have more than one scalar component, temperature, when temperature is, when we discuss about temperature or the thermal field, it is a scalar component, unlike the velocity field. Similarly, when we have salt present in it or solute present in the medium, then in that case, we have to use one more equation which takes care of the conservation of mass inside the concentration equation, which is the convective diffusive equation. And it is based on the law that mass flows always from the mass transfers always from the higher concentration to the lower concentration, and it is proportional to the solute concentration gradient in the medium. Sometimes the mass change in mass or the mass concentration is also affected by the thermal gradient inside the system. In that case, one additional term is also introduced in this equation, which is given by this. This is also known as cross diffusion term or Soret term. Now comes viscous dissipation. So, so far, whatever we have discussed, all the terms in the medium are only taking care of the natural convection, or they are contributing to the natural convection inside the medium, except for this term, this script phi. Now, what that phi can be? It can be viscous dissipation inside the medium. So, it is. It actually takes care of the work done, which is done by the fluid on its adjacent layers. So it, due to which energy is created, and that is contributing to the total energy in the system, and hence disturbing somehow the convection in the medium. So if we have viscous dissipation inside the medium, then we can call it as a forced convection instead of natural convection. Natural convection is a buoyancy driven flow when we have no other external force term in the external term in the medium, which is a source, which is acting as a source of heat. So when we have viscous dissipation, then it is no more a natural convection. However, it is forcing some energy term source inside the medium. Now, here are some boundary conditions for all the three fields: velocity, temperature, and concentration. So first one is the hydrodynamic boundary conditions, where we have three different types of boundary conditions. First one is for impermeable boundary. When we have a rigid boundary, when it is impermeable in nature, then in that case we use no slip condition, where the velocity of the vertical component is 0. Then when we have permeable boundary or a free surface which is exposed to the atmospheric condition, then in that case we can have the boundary condition given like this. So the velocity component of the vertical velocity gradient of the vertical component is 0. Third one is for interface situation, when we have a fluid layer superimposed on a porous layer which is saturated with a similar fluid, then in that case we have an interface condition which is given by Beavers and Joseph. So here the gradient is proportional to the jump in the velocity, and that proportionality constant is given by this coefficient, which is known as Beavers-Joseph parameter. Next, we have some thermal boundary conditions. So there can be different types of boundaries, thermal boundaries: perfectly conducting boundaries, adiabatic boundary, imperfectly conducting boundary, or non-uniform thermal boundary. When we have perfectly conducting boundary, then in that case it is also, we are also call it as isothermal boundary. So the temperature is constant for that case, and that is also known as Dirichlet condition. Mathematically, in mathematics we have three types of different boundary conditions. So that is the first kind. Second one is adiabatic condition, when the temperature gradient across the boundary is constant, given by a constant function. So that is a second kind of boundary, also known as Neyman condition. Third one is imperfectly conducting boundary. There we have combination of the two. So it has some initial temperature, but the temperature gradient is also there across the boundary, and that can be given by some constant function, and that's how it is a mixed kind of condition, and we also call it as Robin condition. Third one is non-uniform thermal boundary. In that case, there is a heated boundary which has some initial temperature, but along its length, the temperature of the boundary will either decrease or increase, and it depends on the parameter eta. So that we call as non-uniform heating or non-uniform thermal boundary. We have analogous conditions for solutal boundary conditions also. When we have uniformly salted boundary, then the solute concentration is given by a constant value, which is also known as Dirichlet condition. Then we have a constant mass flux boundaries. So in that case, the mass flux is given by, again, a constant function. Then third condition is again a mixed condition, which where the combination of the two, the mass flux as well as the difference in the concentration of the layer exactly lying below the boundary and concentration at the boundary, they are given by, again, a constant, and here that's how it is a mixed boundary condition. Here I'll show the effect of having combination of these boundaries when we have a layer, porous layer, which is confined between two horizontal boundaries. So if we have a porous layer which is confined between two rigid boundaries, they may be rigid or permeable, whatever is the case, but I'm only talking about the thermal boundary. So when we have two boundaries, and those two can be combination of two different kinds or same. So in that case, how does the isotherms look like, that I want to show through this picture. So this is a case of a combination of two adiabatic boundaries. So here the two boundaries, both upper one and lower one, both are adiabatic boundaries. So the temperature flux is constant. In that case, the isotherms look like this. Isotherm is a line or a map at which at any point if it see the temperature, it gives a constant value for a given time. So this is for a combination of two similar boundaries, and both are adiabatic in nature. Second one is the case when we have lower boundary as adiabatic boundary and upper one is an isothermal boundary. So whenever we have isothermal boundary or perfectly conducting boundary, then near to that boundary we have a thermal boundary layer, because of which these cells of the isotherms are more concentrated towards the lower boundary, since the lower one is adiabatic in nature and the upper one is isothermal in nature. And the reverse happens when we have lower boundary as isothermal and upper boundary as adiabatic. Here, near to the lower boundary, we'll have a thermal boundary layer. When we have both the boundaries as the isothermal, then in that case, we will have a structure something like this, and we'll have thermal boundary layers at both the boundaries. Through this figure, we can see how non-uniform heating affects the thermal field. So it was the fourth boundary condition that I showed, this one, when the temperature either increases or decreases along the length. So in that case, when we increase that parameter eta, that means if it is positive, then it means that with the length of the layer, with the length of the horizontal layer, the temperature is decreasing. Then in that case, for at the starting phase, it looks somehow like this. The thermal field looks like this. And if we keep on increasing the value of eta, then the thermal field start behaving some like this. So if we reach this stage, then we get a circulation kind of thing in the middle of the layer. that is known as Hadley circulation. And if we keep on increasing the value of eta, then later on you will actually see a circular circulation in the middle of the layer. So that's how the non-uniform heating affects the thermal field. One more preliminary concept or the factor is there, which is known as Overback Bozonisk approximation. This is an approximation which we use very often when we deal with the natural convection system. When we have pure thermal convection, then in that case, the density of the fluid is assumed to be is assumed to be linearly dependent on the temperature of the medium. So this is how it looks like mathematically. But when we have double diffusive system, means we have both the components, temperature as well as solute concentration, then in that case it looks like this. So in that case, the density is linearly dependent on both temperature and the solute concentration. And we use this approximation when we talk about naturally convected system. And when it is associated with Darcy's law, means when we use it for porous media flow, then in that case, Darcy's law gets modified like this. Okay, so the body force term, and this approximation is used only with the body force term. So the body force term is now modified like this because of the Bozonisk approximation. Now let's go to the Darcy-Bénard convection. Before that, we should know what is Rayleigh-Bénard convection. So Rayleigh-Bénard convection happens when we have a clear fluid flow, clear fluid layer. Suppose we have a clear fluid layer and it is confined between two boundaries. Lower one is kept at a higher temperature and the upper one is kept at the lower temperature. So the fluid layer which is near to the bottom plate or the bottom boundary will get heated, and since it's heated now, so its density will decrease, and so it will tend to move upwards. And similarly, the cooler layer which is now at the upper side will now be pushed towards the bottom layer. So this is how a cell kind of structure forms. And the procedure of pushing the hotter layer upwards and pulling down the cooler layer downwards is known as the convection. And mathematically, it is dependent on a non-dimensional parameter which is known as Rayleigh number. And the convection is often seen in terms of some cellular kind of structure which is known as Bénard cell, and that's how the name Rayleigh-Bénard convection comes into picture. Now, when we have a porous layer instead of a clear fluid layer, then in that case, that Rayleigh number which governs the convection in the medium is now modified with the Darcy number. So that Rayleigh number is not same as the Rayleigh number which we have for a clear fluid case. Now it is multiplied with the Darcy number, and it is modified. That's what we should call. So it's modified, and we call it as Darcy-Bénard convection now. So the convection is in the medium is often observed in terms of Bénard cells, and those can be of different shape. Either sometimes it can be in hexagonal cell structure. It can be it can be in terms of convective rolls of circular planform, or sometimes square planform. So this is also an example where silicon oil is heated from below, and after some times we get to see this kind of structures. These are the convective cells, and it's happening only because of this procedure, this mechanism we call as Rayleigh-Bénard convection. Now, convection, up to convection, it is one fact. Second, we discuss about the stability of the flow which can be hampered because of this convection or because of other several factors present in the medium. So through the stability analysis, we get to know about the factors, or we get to know about the condition for at which the instability in the medium tends to start. So there are two analyses which can be done to analyze the stability in the medium. First one is linear stability analysis, and second one is non-linear stability analysis. In linear stability analysis, first of all, if we talk about the stability only, by that we mean that if we disturb the basic state or the initial state by some disturbances, if we superimpose the initial state with some disturbances, then how is it going to behave if it is unperturbed by those disturbances, and the instability is decaying with time? Then in that case we call the system as a stable system. But if in a case when we superimpose some disturbances to the initial state, and when it gets disturbed by some finite magnitude, then in that case and it tends to deviate from the initial state more and more with the time, then in that case we call it as unstable. So stability analysis can be done via two different methods. First is linear stability analysis, and second is non-linear stability analysis. Linear stability analysis is taken care of by the infinitesimal disturbances, where the basic flow or the initial state is subjected only to the infinitesimal disturbances. And that is only because when we linearize the system, and if we have a finite disturbances, then we cannot ignore the higher order terms. So because of that, we superimpose infinitesimal disturbances to the initial state or the base flow when we do linear stability analysis. In non-linear stability analysis, we superimpose some finite amplitude disturbances to the base flow. And what do the two methods give? It is shown here. So through both the analysis, we achieve or we get the condition at which the fluid, at which the system starts getting unstable, or in other words, if I say, it separates the stable and the unstable region. That is more appropriate. So if we follow linear stability analysis, then we get a boundary like this, which is given by this red curve. It also separates the stable and the unstable region. But the thing is that anywhere below this curve, we have the system definitely stable. But above that curve, the system may or may not be stable, because that is the point where the instability starts. But it does not guarantee whether exactly at a point above the curve the system is unstable. But below that curve, it is definitely stable. And if we follow non-linear stability analysis, then we through that also we get to know about the condition or the parameter values for which the system starts or tends to become unstable, and that is given by the dashed curve. That also separates the stable and unstable region, but the difference is that the region which is above that curve is definitely unstable. So the system is definitely unstable for the region which is lying above that curve. So for this region, it is unstable for sure, and for this region, it is stable for sure. But the region which is there in between these two curves is known as the region of subcritical instability. So we can't comment anything about that. We cannot analyze about the conditions or the width of that layer. So we always tend to we always intend to get the condition for which both the curves overlap each other, and that would be the case of supercritical stability. We have many applications of Darcy-Bernard convection in real life, in the field of science and engineering. Geothermal plants is one of them. Here, cooler fluid is injected inside the earth crust, where we have some thermally active source of heat inside the medium. So this is a naturally occurring porous medium. It can be considered as a naturally occurring porous medium, which consists of sedimentary rocks. And deep inside the Earth's crust, we'll have some source of heat, geothermal in the geothermal reservoir, for example. So when we inject a cooler fluid inside that, it gets heated and it is pushed upward through another duct, and then at a heat exchanger, with the help of heat exchanger, we can use that hot fluid, and it gets easier then to collect the steam, and we can use that to drive the turbine of the generator. And that's how this method or this mechanism of natural convection can be used to generate electricity. So we can see the method that the cold water is pumped inside, or it is injected inside the well, which is getting heated in the geothermal reservoir, and the hot fluid in return is sent upward to the surface, which is surface under pressure, and then it heats up the secondary fluid via the heat exchanger, and the steam which is collected is used to move the turbine, and that's how the electricity, this mechanism can be used to generate electricity. Now I'll come to the problem which we have solved. Here we'll consider a more general case. So instead of taking a horizontal layer, we are considering an inclined layer. So the angle delta can have a value 0, which means we have a horizontal porous layer, and it can have a value pi by 2, which means we have a vertical porous layer. So, and in reality, in real life, inclinations are always possible. That's why considering such a system is more realistic, and it facilitates a generalized model which can be used for any particular inclination. Not only that, the two boundaries which are used across the layer are the permeable boundaries, means the pressure at the two boundaries are constant, and both are isothermal boundaries as well as isosolutal boundaries, means the temperature and the concentration at both the boundaries are constant. However, there is a difference between the temperature and solute concentration across these two boundaries. So the lower one or the bottom one is having higher temperature as well as higher solute concentration, and that's how the mechanism of natural convection can be expected. Delta is the angle at which the layer is inclined to the horizontal. Now, as I have already discussed about the governing equations, so now it can be a little easier to understand what are the equations we have used to govern the convection inside the fluid saturated porous layer here. So up to this, it's exactly using Darcy's law, where we have both the components, thermal as well as solutal. But since we have inclination in the layer, that's why this extra factor is also there, which takes care of the two components of that vector, which describes the direction of the flow. Then the third equation is the conservation of energy, and the fourth equation is the solute concentration equation. And since we have assumed permeable boundary, means the pressure at both the boundaries are constant, we end up getting these two hydrodynamic conditions for our system. And these two conditions can be derived by using that constant pressure condition in the equation of continuity, and by using Darcy's law also. Now, these are the scaling variables which we have used to parameterize the equation, and the given equation is already in a non-dimensional form. It's in the we have a set of non-dimensional governing equations, and to obtain those equations, we have used these scaling variables. After parameterizing, we have three non-dimensional parameters which are involved in the system, and they represent three different factors. Ra is the Rayleigh number, rather Darcy Rayleigh number, which governs the convection inside the medium, and it is mathematically the temperature gradient across the two layers, across the two boundaries. N is the buoyancy ratio. It is a ratio of the buoyant force due to the concentration field to the buoyant force due to the thermal field. L is the Louis number, which is the ratio of the thermal diffusivity to the solutal diffusivity. Now, first of all, we talk about the base flow. So base flow is the one which is which was there initially with us before we perturbed the system, before we introduced the disturbances. So this is how the base flow, basic flow profile, basic pressure, and basic temperature and concentration look like. So basic velocity looks like this, and it is due to the horizontal components of the thermal and solutal fields. This delta, sine delta term is because we have considered inclination in the system. And both temperature and concentration fields at the for the basic flow are linear in nature, and they decrease with the height of the porous layer. Now we introduce the disturbances in the medium, and this is how it is done. Here epsilon is the infinitesimally small parameter. It is a parameter, perturbation parameter, which is very, very less than 1, and because of that, this disturbance is infinitesimally small. Then we introduce, as I said, the convection in the system are often observed in terms of convective rolls. It can have different shape. So, considering periodic convective rolls as the mode of disturbance in the system, we assume these disturbances. So, this is a vector U, which will have three components, U, V, and W. So, this is how they look like, where gamma is an angle which is made by the rolls axis. So the convective rolls, or the disturbances which are assumed in terms of convective rolls, are inclined to the base flow at an angle gamma. So we, along the layer, we have the base flow, and the convective rolls are inclined to that base flow at an angle gamma. So because of this, that fact, this angle gamma has been introduced, and this is how the disturbances look like. Now, making use of the normal mode analysis, and also assuming the stream, also introducing the stream function formulation, since we have only two non-zero components of the convective road or the disturbance field, and the third component will be 0, because the disturbances are of circular plan form. They are two-dimensional rolls. So because of that, we can introduce stream function formulation, and using normal mode analysis, we can assume the disturbances in this form. We also make use of the square type transformation, and that is just done in order to reduce the parameters. Now that we already had a Rayleigh number, then buoyancy ratio, Louis number, and the angle inclination angle of the layer. And now again, we have one more angle, which is the angle at which the rolls are inclined to the base flow. So we have so many parameters. So if we make use of square type transformation, then we can reduce that number, reduce the number of parameters. So we introduce a new parameter S, which can be treated as a modified form of the Rayleigh number. Okay, so logically, it will now govern the convection in the medium. And one more parameter is introduced, which is phi, and this is how it is related to the angles delta and gamma. Now, using all these things in the governing equation and linearizing the system, this is what we get. This is the final eigenvalue problem which we have obtained. It is a system of 3 second order coupled ODEs which have eigenvalues also. So omega and S are the two eigenvalues. Omega is the growth rate, or since we have already ignored the imaginary term of the growth rate, so it is actually the angular frequency, positive value of which will get us the oscillatory convection or oscillatory modes or the traveling modes, and zero value of that will get us the stationary modes or non-traveling modes. So that is also one of the eigenvalues along with S, which is the parameter governing the convection inside the medium. So this is a system along with these boundary conditions. Now, since we have a system of ODEs, we can solve this using, and it also involves eigenvalues. We can solve them using shooting technique, and it can be coupled with Runge-Kutta method of higher order. After that, I'll show you the results, which are the neutral stability curves. Neutral stability curves are the ones which I showed while explaining about the linear and the non-linear stability. So this boundary is actually, it represents the marginal stability state. So that's what we are getting here for this problem, for the present problem. So here we can see, since we have considered inclined layer as well as permeable boundaries, so because of that, we have the neutral stability curves in some different form. It's not like the conventional form which we know for the classical Rayleigh-Bénard or Darcy-Bénard problem. So here you can see that since the parameter phi represents the angle of inclination, so we can see that for different angles of inclination of the porous layer, the neutral stability curves behave differently, and it is most stable for this layer. So higher the stability curve, stable is the system, because for that the stability region will be more as compared to the other rolls which are other curves which are lying below that. So this one is the most stable in that case, which is corresponding to the layer which is vertical to the horizontal. I mean, which is exactly vertical, pi with angle pi by 2. And phi equal to 0 corresponds to the horizontal layer. Not only that, we also see that for some of them, excluding that higher one, for all of them, we have some branches also of those neutral stability curves, and those branches are corresponding to the traveling modes. Now, this is for the case when we have buoyancy ratio negative as well as less than 0. It means that the mass flux and the temperature flux, concentration gradient or the mass gradient and the temperature gradient, both are acting in the opposite directions. And the solute concentration is lower in magnitude than the thermal gradient. So for such a case, we have the instability occurring in both stationary as well as oscillatory modes for all the inclinations of the porous layer. As we can see, at all the inclinations, we have additional branches that correspond to oscillatory modes. The solid curves correspond to the stationary mode, and the dashed one correspond to the oscillatory mode. So this is for the case when the solute concentration, solute gradient and mass temperature gradient both are acting in opposite directions. When we have both the forces, both solutal buoyancy and thermal buoyancy acting in the same direction with the same intensity, then in that case, the scenario is little bit different. Here we can witness the oscillatory instability only for a few inclinations. And we not only that, one more factor can be observed, that for up to a certain value of inclination, the instability is observed in terms of infinite wavelength mode. So the minimum value of the this parameter SA gives us the threshold value beyond which the system is unstable. So for certain values of phi or the inclination, we can see that the critical value or the minimum value of the parameter S is coming out to be 0. So for such cases, since A represents the wave number, so for such cases, the instability is seen in terms of infinite wavelength mode. So that is also one of the observations we made for this problem. And it is same for the aiding buoyancy case. This is opposing buoyancy case where both the buoyant forces are acting in opposite direction, and in this case both the forces are acting in the same direction, so we call it aiding buoyancy case. In aiding buoyancy case also, up to a certain value of phi, we can observe the instability occurring in terms of infinite wavelength mode. However, in aiding buoyancy case, the oscillatory instability is not observed at all the inclinations. It is observed only up to a certain value of phi, which is known as a critical, which we can call as critical inclination angle. And up to that inclination angle, we also observe the instability in terms of infinite wavelength mode. This figure represents the case when we have thermal diffusivity comparatively much higher than the solute diffusivity. The last case was for the last case corresponds to, this case corresponds to the magnitude of thermal diffusivity much less than the magnitude or the intensity of solute diffusivity. But here the intensity of thermal diffusivity is much higher. So here, for opposing buoyancy case, we observe the same thing which we observed for the last case, but here we have even some more branches in the primary branch also. So if we call it as a primary branch and this dashed one as the secondary branch, we have a sub branch also for almost all the angles except for the pi by 2 and for 0. So these branches correspond to oscillatory instability. Since it is in primary mode, since it is in primary branch, so it is also represented by solid curve, but they correspond to oscillatory instability, which is not the case in aiding buoyancy case. So for any value of Louis number, whether the thermal diffusivity is more intense than the solutal diffusivity or not, aiding buoyancy case is same all the time. But in opposing buoyancy case, the scenario is different when the thermal diffusivity is more intense than the solutal diffusivity. Here, the instability is even initiated with the oscillatory mode, which is not a regular or a thing which is observed most commonly in the Darcy-Bénard convection. So that is a kind of exception. Now, coming to the concluding remarks. So the convective flow we have observed to be least stable in the horizontal porous layer case when we have an angle 0, and it is most stable when we have vertical porous layer where angle is pi by 2. And the convective instability at all the inclinations is always initiated by the non-traveling modes. Means in all these cases, since we don't have any other primary branch, any sub branch in the primary mode, so in all these cases except for this one, the instability is initiated by the non-traveling mode, also known as the stationary mode, except for this case where we have opposing buoyancy case and the thermal diffusivity is much higher than the solutal diffusivity. The third conclusion is that the instability grows with the increasing buoyancy ratio at all the inclinations. However, in case of vertical porous layer, it progresses non-monotonically. And that is only for the case when the solutal diffusivity is dominant over the thermal diffusivity. And with that, I conclude my talk. These are some of the references. Thank you. This work is actually published in Physics of Fluid in collaboration with my supervisor, Professor P.V.S.N. Murthy. Thank you, ma'am. I think it was a long talk.
It was a nice presentation, Rashmi.
Thank you. Thank you, ma'am. Thank you for giving me this chance. Thank you, ma'am. The pleasure is all mine. Thank you.
Thank you so much, ma'am. Thank you. Thank you, Rashmi, for being here.
Thank you, Chanika.
Bye.
Bye-bye.